In this video, I'm going to try to explain the relationship between forces between particles and melting and boiling point. Now, if we don't have our full knowledge of those forces between particles, this is a bit of a tricky concept to get your head around. However, there's time to get there. Basically, melting and boiling points are a really good indicator of the strength of forces or bonds between particles. That's because to melt something or to boil it, you need to break at least some of those bonds. So for melting, it's breaking some chemical bonds, and for boiling, it's breaking whatever ones are left over. So it's a measure of strength because the higher that temperature, the more energy is required to actually break the bonds. So that idea makes sense. There's a bit of a, I'm trying to remember the word, hierarchy of strength for our bonds. Our ionic bonds are our strongest. They're an electrostatic attraction. Positive charges and negative charges in 3 dimensions. They're directional forces. They're really, really strong. We would expect ionic compounds to have very, very, very high melting and boiling points. And that's what we observe. They're in the thousands of degrees usually. That is influenced by the nature of the particles and the size of them. So the more positive or the more negative, so the bigger the ionic charge, the stronger those forces will be. And the smaller the ions are, the closer together they'll be, so the stronger those forces will be. So the higher the melting and boiling points are going to be. The next strongest are called hydrogen bonds. This is when you have a highly electronegative element like oxygen bound to hydrogen in a polar molecule. And what that allows is a special bond called a hydrogen bond to form between this highly electronegative element of one molecule and the hydrogen of the next one. And it's very strong. It's the strongest of our intermolecular bonds. So these are discrete molecules, not ions, and they have a strong bond between them called a hydrogen bond. This is why water has a very high melting point for such a tiny molecule. Even though it's polar, it should be a gas at room temperature because it's so little, it's got such a small electron cloud. So not only are there permanent dipoles between the two sides, the slightly positive side and the slightly negative side of neighbouring molecules, so it's got permanent dipole forces, it's also got hydrogen bonds which are even stronger. That's a lot of relatively strong forces acting there. So that leads me to my next one, which is our permanent dipole. Polar molecules have got higher melting or boiling points than you would expect for the size of the molecule. So if you looked at another one that had the same molar mass, they should have the very similar melting and boiling points, but they don't. And that's because they form permanent dipole forces between them. And those are our second strongest intermolecular force. But they're only about 1/10 the strength of a hydrogen bond. So they're quite a lot weaker. So if you see anomalies and trends of melting and boiling points of molecules, check if it might have hydrogen bonding involved, because that's often the explanation. It's a stronger bond, so it requires more energy to break, so that increases the melting, or if it's talking about it, boiling point. Stronger forces require more energy to break. So remember that from year 12, bond breaking is endothermic. It requires heat energy. The weakest are your temporary dipoles, also called London dispersion forces, sometimes called van der Waals forces. They're very weak. They come and go. The bigger the molecule, the more likely they are to form. So a larger molar mass will have a higher melting and boiling point. And this is because with a larger molar mass, you get a larger electron cloud. A larger electron cloud is more likely to have uneven distribution of electrons. They have what are called temporary dipoles forming. So if you're looking at pure substances, the melting and boiling points of those, excuse me, look at the nature of the particles. Are they ions, molecules, atoms? What are they? Well, in year 13, they're going to be ions or molecules. Then, are those molecules polar or non-polar? If they're polar, you've got permanent dipoles. If they're non-polar, you've got temporary. If they're polar but have really unusually high melting and boiling points, check if they've got hydrogen bonding in them. I have done a video on that as well, so I won't explore that anymore here. So that gives you the type of forces, which then you can relate to the strength and relate back to our melting or boiling point. But what happens with a mixture? These are the really hard questions. This is to do with the attraction between the different types of particles. So once you've got your two pure substances that are in the mixture worked out, you go, well, how do they interact with each other? So if I had pure water, basically pure water lines up a bit like this. I'm going to quickly make another molecule actually, because it does create a bit of three-dimensional structure here, a three-dimensional lattice, a bit like silica, so a bit like glass, where there's a lot of bonding happening here. It doesn't just have to be one. We could have a hydrogen bond here and here. We could have a hydrogen bond here, and you start to get a three-dimensional structure. Maybe this one's sitting out here in space. So we get this more complex three-dimensional structure. And if it was ice, then it is very much like glass. If you think about dropping a piece of ice on concrete, it often shatters and cleaves or breaks in the same way that a piece of glass would. I suggest you don't try it with glass, please, because that's a bit harder to clean up. Icy roads are actually dealt with using salt. They have grit for friction, that's physics, we'll leave that to physics, but they also have salt in there. And the reason they put salt in there is it lowers the melting point. It turns that ice into water, even if it's still below 0 degrees Celsius on the concrete, on the tarmac. And once it turns into water, of course, you can drive on it quite safely. Well, this is actually some really cool structure and bonding. The lowered melting point is because of the relationship. I've only got a chloride ion here, I'm sorry. Is because of the relationship the chloride ion has with the water molecules at the edge of, I'm just going to give myself a bit of space here, at the edge of the ice crystal. So along comes this, and it's an ionic compound. It's going to have a stronger attraction to the delta positive side of the water than the hydrogen bonds. It's a stronger attraction. And then this is going to get surrounded by water molecules, the delta plus towards the negative ion. Sodium, oh look, let's just choose this one arbitrarily as being sodium, would be surrounded in the opposite way. Now these water molecules can no longer be part of the crystal. Their attraction to the chloride and the sodium ions is greater than their attraction to each other, so these ions get in the way. That mixture has affected its melting and boiling point, lowering it, because once these surround these ions, they're actually in the liquid phase. They've been removed from the solid and therefore are going to move around together sort of as a bit of a group. Because they can move, they're liquid. The bonding between the water molecules has been broken.